Good afternoon, everybody. So we're going to start the class. The class for today is finding the roots of equations. So like we had in our previous classes, I would start the lectures. Then if you have any questions, don't hesitate to drop it in the chat. From time to time, I'll check the chat and I'll try to answer your questions. Before we begin today's class, I want to go over an aspect of what we did last week, Monday. So when we got to the roots of a quadratic equation, there was a student that asked that I should do the manual calculation. So I decided to do it. So I'll just go over it before I start today's class proper. So we all know that this is the formula to get the root of a quadratic equation. Then when you plug in the values, you would arrive at this equation. Then the square of this is actually this. So in the last class, I kind of made a mistake. So this is the square of this. And when you subtract it from 12, you get this. So this is like your final result. Then you have x1 and x2. x1 is, there's a plus here. Then x2, there's a minus here. Then when you do the arithmetic for x1, you're going to get this. Then for x2, you're going to get this. Actually, when you run it in the code, you're going to get an error. Because last week we were talking about errors. So the error is due to subtractive cancellation. That is, in this part, we don't have any error because you are a negative and negative is, you have negative, then it's just as if you're adding together. But this, you're subtracting, there's a positive sign here and there's a negative sign here. So it's because you are subtracting very two close numbers together, there's going to result in a kind of error, because when you do the math, actually is going to, the amount of decimal places you're going to have is going to be very much. Then for single precision, the decimal places won't cover it. But for double precision, the decimal places will cover it. So the double precision is much more accurate than the single precision. Okay, so that's that. So let's move on to this lecture, what we have for this lecture. Okay, we're going to be dealing with the roots of equations. And in the last class, we actually did the roots of a quadratic equation, and we know that giving an expression of this format, we know that the root is given by this representation. So you are all familiar with that. And there are some functions, or there are some expressions that you have to reduce it. When you are giving the question, you have to reduce it to finding the root of the equation. So what's basically the root of the equation? The root of the equation is like if you have a function, like if you have this function, so I'm just giving an example now. So if you have this function, let's say 2x squared let's say 2x squared plus x is equal to 2. So if you have this equation, right, this equation, you can reduce it to finding the root, and you're asked to find the value of x. If you're asked to find the value of x, you can reduce this expression or this equation to the root of, and to finding the root. And how do you do that? You're just simply going to subtract both sides by 2, then you equate it to 0. So if you are given this expression and you are asked to find the value of x, you can reduce it to finding the root of the equation by simply subtracting both sides of the equation by what you have here, then equating it to 0. So the root is you are finding the value of x when the function, so let's name the function f of x, when the function is equal to 0. So that's simply the root. You're finding the value of x when f of x is equal to 0. So let's go to, as an example, let's go to the model of the falling ball. So in the first class, when we started the first lecture, we actually we derived this model, and this is the model of the falling ball. And if you are asked to calculate the velocity, v is the velocity, m is the mass, g is acceleration due to gravity, c is a coefficient, a constant coefficient, then t is a time. So if you are asked to find the velocity of the ball, it's pretty much straightforward. You can all do that. But in a case where you are asked to find, let's say you're asked to find c, the constant c, it's the solution to that problem is much more difficult because you have to actually make C the subject of formula. And we are going to, you have to make C the subject of formula. So we are going to try to do this, then we see what happens. But if you are asked to find C and you are giving all of this, you are giving the velocity, you are giving mass, you are giving the acceleration due to gravity, and you are giving T, and you are asked to find only C, that solution is actually much complex, which we'll be saying. And in this case, you cannot use analytical solution to solve it. So we're going to do an example. So you have to rely on numerical methods. And remember that this course is numerical methods with MATLAB. And I explained in the first lecture that the best solution to any equation is the analytical solution, because the analytical solution is like the exact and it's very, very correct. But sometimes the analytical solution, you may not be able to actually get the analytical solution. So we have to make use of the numerical methods or the numerical solution. So in this example, we are going to be doing that. So in order to actually solve it using numerical solution, we are going to reduce the question, because the question now is asking us to get the value of C where all these constants are known. We are going to reduce it to finding the roots. And remember in the first example I did, if you have this expression and you're asked to find the value of x, you can reduce it to finding the roots by subtracting both sides of the equation by 2, then equating it with 0. So we want to reduce this problem also to the roots, to getting the roots of the equation. So in order to do that, we are going to subtract both sides. This is our original equation here. We are going to subtract both sides of the equation by, we subtract both sides by v. Then after that, we'll make it to be equal to 0. Then we'll create an expression f of c. Then the root of this equation is the value of c when f of c is equal to 0. So that's simply the root of the equation. So let's do, and to get the roots of the equation, for this class, there are lots of methods. But for this class, we are going to consider 3 methods. There's a graphical approach you can use. There is a bisection method, and there's the first position method to get the root of the equation numerically. So in this class, this is what we're going to be basically doing. Then these methods, they are called the bracketing method because they start with initial guesses. So you guess the roots, you guess the point in between which the root is available. Then from there, you begin to narrow your guesses and all that. So we are going to do an example. The, the first method we are going to use is the graphical method. So we are going to use the example I started with. This is the model for the falling ball, which we derived in the first lesson. And the question is asking us to find C, to find the coefficients, the air resistance coefficient, and it's giving us the other values. So we know M, we know the velocity, we know time, and we know G, which is the acceleration due to gravity. And the question is telling us that we should find the value of C, and we should find the constant C. So, like I said previously, you can just substitute all these parameters because we are giving all these parameters. So you can just substitute it into the original equation and you try to find the value of C and you make C the subject of formula. But I'm assuring you that if you actually do this and you try to make C the subject of formula, it's not possible. So after the class, I would I would encourage or um, I would suggest that you try it. Just try to find the value of C and just bringing out C to the other side and making the C the subject of formula. You would see that it's not possible. Like you cannot do that. So if you are doubting what I just said, if you're doubting and you feel that okay, I can actually do this. I can make C the subject of formula and just find C straight away. You can try it, and if you are able to get it, you can just send me a mail or something that I was able to make C the subject of formula and I was able to find C. But I assure you that it's not possible. You cannot solve for C in this way, and you can not get the value of C using this method. So I'm encouraging you to try it and to see for yourself that it's not possible. So in this case, we wanted to solve for C and I'm telling you that it's not possible. So if we had been able to solve for C here, then that would be our analytical solution. But this is in this example, so somebody said for C to be at exponential is not possible. Yes. So yes, you're very correct. It's not possible because of this exponential. But for others that think they are doubting that, okay, it's possible, just try it and you'll see for yourself that it's not possible. So in this case, if you had been able to get the value of C, would that would be the analytical solution. That would be the exact solution. But in this example, we cannot even find the analytical solution. So we have to go through the numerical solution. Like when we started this course, I told you that there are some equations that you would not be able to solve it analytically. You cannot get the exact solution. So that's why we need to fall back to the numerical solution. So we're going to use the numerical solution to solve it. Then the way we'll solve it is that we are going to reduce the question to finding the root of the equation. So the way we do it is that this is our original equation. So we subtract both sides by V. If you subtract both sides by V, you are going to get this. Then you equate it to 0. Then you create a function f of C. So we are reducing the question to finding the roots. And the root, the value of C, where f of C is equal to 0, that's the root of the equation. And that is the value of C we are looking for. So let's do that approach. Now, we've already reduced the question to finding the roots of the, to finding the roots. Then we put in the values. We're giving all these values. Then when we multiply this by this and we do this arithmetic here, we are going to arrive at this equation. Now, we want to find the value of C at which f of c, the function, that at which the whole of this is equal to 0. So the first method we are going to be considering is the graphical method. So for the graphical method, let me go to Excel. So I'm going to plot it using Excel. So basically what I'm going to do is that I'm going to create different values for C. Then I'm going to use this expression here. So here is the, to convert it into Excel, Excel format. So I'm going to use this expression here to actually solve for it. So I would have different values of C. So this expression here is the same thing as this expression here, but in Excel format. So this is 668.06 divided by C, then 1 minus exponential. So this is the function for exponential in Excel, minus 0.146843C, then minus 40. So this is what I'm going to use. So let me go to Excel now. So I'm in Excel now. So we are going to be using the graphical approach to solve this problem. So I have C here, and I have different values. So you're going to type in some values for C. You can start from a negative number, but I chose to start from 1. Then you find the f of C. So to find the value of the function when C is equal to 1, I'll place the cursor here. Then in this box, I'm going to type this. So this is the function, but in Excel format. So when I click enter, you arrive at the function. Then when I just drag it, I will arrive at the function for each of the values. Then now I'm going to plot it. Remember, we are using the graphical approach. So I would plot it now, and so when I plotted this function. So this is the function at different values of C. So the x-axis is the C, while the y-axis is the value of the function here. Then the root of the equation is at the point where the value of C when f of C is equal to 0. So this is f of C here, and this is C. So the value of C where f of C is equal to 0, it's around this point here. So that's the root. So that's like what we are looking for. But it's not so clear here. So let me try to expand it, the graph. It's not so clear. So the root, let me say it again. The root is the value of C where f of C is equal to 0. So f of C is equal to 0 at this point here. So we are not very clear which exact point. The graphical method is an approximate method. So we are not so clear which exact point. So let me try to reduce the plot, because looking at observing the values, you can see that you have, when C is 14, you have a positive number. Then when C is 15, you have a negative number. So we are kind of aware that the root is going to be between 14 and 15, between 14 and 15. So let me format the axis. Uh, Let me say the maximum is 20, then the major unit, let me say is 1, so that we can really see it. Okay, so when I formatted the axis, from these values, you can see that the root is going to be between 14 and 15, because here you are in the positive side and here you are in the negative side. So the root is somewhere in between. So if we narrow the graph and we plot it, but in this case, we're just plotting the value of C between 14 and 15, because we are aware that the the value of C is between 14 and 15. So I just want to narrow the the plot. So I would edit. So I will narrow the plot between 14 and 15. So A15 and A16. So A15, then A16, because we know that the root is between these values. A15, then B16. Okay. So when we narrow the plot, we get this. Then let me change the axis. Let me change it. Um, the Let me say the maximum should be 15. The minimum should be um, let me say the minimum should be 14. Then the maximum should be 15, because we want to actually get the exact root. Okay, so when we do it this way, let me just reduce it. So we know that the root is between 14 and 15, and we are not really sure. So when I'm just narrowing it down. So this is like the full plot. So we know that the root is between 14 and 15. So I'm just plotting from 14 to 15 here. So we know that the root is somewhere here. So let me change the axis so that it's going to be uh, 0 0.1, 0 0.1 plus. Okay, so so I've changed the axis now. So from this plot, which I narrowed down, I can say that the root is at 14.8. So remember I said that the root is the value of C when f of C is equal to 0. So simply when the graph touches the x-axis. So let's say that the root is 14.8. So from the graphical method, so this is using the graphical method to solve the problem. So from the graphical method, we're able to see that the root is 14.8. So I think you all understand what I did. So the root is 14.8 because this is where the line touches the x-axis. Let me go back to the notes now. Okay, so from the graphical method, we discovered that the root is 14.8. So I think you'll understand where I got that. So in order to validate what we just got, and when I started, I'm saying that there's no analytical solution for it, because if you try to do this, you're not you'll not be able to get it. So you have to make use of the numerical method, and this is the numerical method trying to make use of. So from the graphical approach, we said that it's 14.8. So in order to verify if we are correct, we are going to place, instead of, there's a C here and there's a C here. So instead of the C, we are going to replace it with 14.8. If we do that and you calculate it, you're going to get this expression, which is close to zero. Remember, it's supposed to be zero because we said let f of c be equal to zero. So we're kind of close to zero, so we know that at least we are close to the answer. And another way to verify if what you got is correct is to actually, this is the original equation, this is the model of the falling ball. So the answer you got, that's 14.8, you substitute it here and you substitute it here. So if you do that, you are going to arrive at this. And from the question, V is 40. So this is close to 40. So we know that at least we're a bit close to the solution. So this is the graphical method of finding the solution. The graphical method is not so accurate actually, and is not so precise because it's just an estimate. And in a case whereby, because I'm using a computer to plot it, I'm using a computer to plot the graph. In a case where you have to use your hand to manually plot the graph, it's going to be much more not precise because you have to plot it by hand, and you're not, because we're using a computer, we're using Excel, so that was why we're able to really get very close to solution. But it's not so precise, and it would help us in other methods as we are going to be seeing. So I just want you to note that the true value of the root is 14.8001. Then for the graphical method, we were able to get 14.8, which means that we are close to the solution. If you ask me that, how did we arrive at this value? We arrived at this value from trial and error because, like I said, there's no analytical solution. There's no exact solution for that. So in order to arrive at this value, we're just trying and error. So we put in 14.800.8011. Then we put 14.8011. Then we got 40 exactly. So we know that that's how we know that this is the root of the equation. So the answer to this particular question is that you should find the air resistance coefficient C when all these parameters are given. So the answer is that C is equal to 14.8. Using the graphical method, we got 14.8. So that's the solution to this problem. But the graphical solution is not accurate. Using a computer, like what I just did, you can be very close, and you can go close to the solution. But in general, if you are plotting it by hand, it's not so accurate. So we go to the other methods. And the first method, the second method is the bisection method. And the bisection method simply makes use of the fact that the root occurs when there is a change in sign of the function. So the bisection method, actually, what it does is that you're going to have a guess. You're going to have two guesses. So the first guess is XL, that's the lower limit, while the second guess is XU, that's the value of X at the upper limit. And let me go back to Excel so that I'll be sure I'm explaining this very well. So what the bisection method does is that you're going to be given two guesses. You know that it's building on the fact that the root occurs when there's a change in sign of the function from the positive to the negative. So this is the positive function, this is the positive side of the function, and this is the negative side of the function. We know that the root occurs at the point where the line touches the x-axis. So the bisection method is saying that you are going to have two guesses. The first guess is the value of x or c in the part where the function is positive. Then the second guess is the value of x or c when the function is negative. So you have two guesses. So the first guess, like I said, which is the lower limit, is the value of the function when it's positive. Then the second guess is the value of the function when it's negative. So after you have gotten those two guesses, or after you've been given those two guesses, you begin to narrow down, the roots down. So I'm going to explain how you're going to do that. So like I said, the bisection method, you will start with two guesses. You'll be giving the two guesses, or if you are not giving the two guesses, you are going to use the graphical method or the graphical approach to kind of guess for the two values. So the lower limit is when the function is positive, the value of x when the function is positive, while the upper limit is the value of x when the function is negative. So you can just guess two values. Then you make sure that the value of the function at the lower limit multiplied by the value of the function at the upper limit is less than 0. So why is this so? It is so because remember, the first guess is the value of the function when it's positive. So if this is positive, then this second one is the value of the function when it is negative. So when you multiply a positive with a negative, you're going to get a negative, which is less than 0. So you make sure that your two guesses, when you evaluate this function, is less than 0. So let me describe the algorithm to do that, or the pseudocode to do that. The first the first step is that you're going to be giving guesses, or you're going to choose guesses xl and xu such that when you evaluate this function is less than 0, so it's negative. Then after that, you will estimate the roots by performing this operation. So xl, that is the value of x at the lower limit, then xu, the value of x at the upper limit divided by 2. So we approximate this. We say that let the root, xr is the root. So let the root be, or let the estimated root be this. Then after that, you are going to make 3 evaluations. You are going to check, you are going to evaluate this function. This function is the value, is the function at xl. Then this is, you're going to evaluate the function at xr. Remember, we've calculated xr as this in the previous step. Then if it's less than 0, that means that the root lies in the lower subinterval. And therefore, you're going to set the root to the upper limit. So you're going to set the value you calculated here to the upper limit. Then if this expression you calculated here is greater than 0, that means that the root lies in the upper interval. Then you should set the lower limit to be equal to the value you calculated here, and go back to step 2. So go back to step 2 and return to step 2. So in this case, you return to step 2, and in this case, you return to step 2. Then if you evaluate this and is equal to 0, that means that the xr you calculated is the exact root. Then you terminate the equation. That's basically the algorithm. So I'm going to be using an example to explain it further. But the summary is that, first of all, you'll be given initial guesses, 2 guesses actually. You calculate the estimated roots with this expression. Then you evaluate this expression here. So this expression is written as this expression and this expression. So if this expression is negative, that means that you should make the upper limit to be equal to the value you calculated here. If it is positive, you make the value you calculated here to be the lower limit. And if it's zero, that means you are done, that this SR is the correct root, then you terminate the expression. So we are going to be using, we are going to be doing it using, we're going to use the bisection method, and we're going to write a computer program that will do it for us. So we're going to solve it by hand, then later we use a computer program. So the first step is to choose x of the lower limit and the upper limit. So this lower limit and upper limit, you are going to be given. And if you are not given, you would have to guess on your own. And you guess in a way that the value of the function at the lower limit plus the value of the function at the upper limit is less than zero. So this is the lower limit and this is the upper limit. So we are sure that the root is between this point, but we don't know the exact point. So step two is we are going to calculate the root as the midpoint. So this expression simply says that the root is the midpoint between these 2 points, and we got 14. Then we got XR as 14, which is our estimated root. Then we evaluate this function. So this function is the value of the function at XL and the value of the function at XR. XL, the lower limit is 12, so you have F12. Then the root, which we calculated here, is 14. So we have 14 here. Then we simply put in place of C, we're going to put 12 and 12. Then, yeah, we're going to put 14 and 14. So we've gotten our F12 and F14. So the value of the function at 12 and the value of the function at 14. So when we multiply it together, we got, this is a positive number. So a positive number indicates that the root is in the upper subregion. So that means that you're going to set the lower limit to be 14. So in the next iteration, this is the first iteration. So because we have a positive number, so this is saying that in place of the XL you have, previously our XL was 12 and our upper limit was 16. So since we got a positive number, it's saying that you should set the lower limit as 14. So the lower limit changes to 14 while the upper limit is still the same. So I have less than 1 minute. I'm going to end the meeting now.